Hello and welcome to this last chapter in the course of machine dynamics, and this chapter is entitled Blade Vibrations. So when we consider blades, then there are two kinds of blades in a turbine. So the first one are stator blades and the second one are rotor blades. And for the rotor blades, we will study the influence of centrifugal forces. But first, in this video, and I would say also in the next video, I'm dealing with stator blades. Well, for the stator blades, the problem is similar to that we saw in the last video, or in the last two videos. Namely, we are dealing with continuum vibrations. And then the question is, what kind of continuum vibrations matter here? And there are two types of loads possible for stator and for rotor blades. The first one is a bending load, and the second one would be a torsional load. And what one can show is that for torsion, the first natural frequency is in general higher than for bending, and therefore, well, we will consider torsion a little bit only. I would say nearly. We will always consider bending, but neglect torsion. But in the last video, where I'm dealing with external excitations and how to design these blades so that they resist the external excitations coming from dynamic loads, we will also deal, of course, with torsional vibrations. But for the other, there will be 4 videos. For the first 3 videos, everything is about bending loads. In the first 2 videos, I will talk about stator blades, and only in the third video, we will then switch to rotor blades. It will need 3 videos, or 2 videos already for the stator blades. In the first one, in this video, I will derive the equation of motion and then solve it for a stator blade. And then we will see that, well, there are some difficulties inherent due to the difference in the boundary conditions when compared to the previous videos. And therefore, the derivation of the orthogonality conditions is quite involved. This will be the subject of this video. And in the next video, I'm talking about the natural frequencies, especially the first natural frequency, and how to approximate it, how to obtain bounds for the natural frequencies. So in this chapter, the hidden story behind is, while you have seen the exact theories for continuum vibrations in the previous 2 videos in the previous chapter, namely Bernoulli separation method and wave equation or wave interpretation. In this chapter, we are opening the way. I'm not saying we are dealing with in completeness, because that needs other courses, for example, a course on computational dynamics, but we are opening the way to approximations. So in the second video, I will talk about approximations for the first natural frequencies. In the third video, we derive the equations of motion for moving rotor blades, so blades that are mounted on a rotor. And we study the influence of the centrifugal force. And in the last video, we see also approximation methods, but methods to design blades and to compute the answer to external excitation. So nearly everything is about bending. The argument is repeated here once again. So the torsional frequency is, the first natural frequency is in general higher. It is nearly independent of the rotational velocity. So the answer here for rotor blades already answered, already given here. And therefore, they appear only in the fourth video in this series of videos for this chapter. So there are 2 objectives here. The first one is to study natural frequencies. As I said, the first 3 videos will deal with that point. And the last one is then about the amplitudes of forced vibrations, so about external excitation. Now, let me come, well, to the derivation of the equation of motion for stator blades. But before I derive the equations of motion, it's necessary to state some assumptions here. So we are dealing with, or we want to deal with, the free bending vibrations of stator blades here in the first two videos. The assumptions are that we can apply classical rod theory so that we can model our blade as being basically a one-dimensional object where the length scales in the other two directions, so in plane directions, so in the vertical and in the lateral direction, are relatively small, and the changes that occur there are relatively small, so that we can deal with beam theory. Yeah. So then there would not be only bending of beams, but there could be also torsion, and torsion and bending can be coupled. But here we assume that the center of gravity and the shear center are nearly identical, so that we can uncouple bending and torsion. And as I said, we are dealing with bending vibrations here only. And then usually these blades, they are twisted, and due to this special shape of the blades, the principal axis would then become position dependent, or space should be assigned with a space-dependent coordinate. And this will be excluded here, so we simplify the problem a little bit. When compared to reality, we will use non-twisted, or we will consider non-twisted blades where the principal axis of bending are then space-independent. So the principal axis for the second moment of area that is needed for the bending stiffness. So then we are left with equations of motion in the direction of principal bending, so in the principal axis. We need, well, that's a short summary of what you have seen in the previous chapter. We need the equation for the beam deflection. So we have the bending stiffness, Young's modulus times second moment of area, times the second derivative of, there is one of the principal directions indicated here by the displacement W, and we take the second derivative, partial derivative with respect to space, and that's minus the bending moment, bending torque. We have the second derivative of that equation that leads to the second derivative then of the bending torque, leading to the first derivative of the shear force, and this yields then the load and could be distributed on that beam, the vertical load. And for that vertical load, we put in the inertia force according to D'Alembert's principle with a negative sign. Mu would be the product of mass density times area, and the second derivative with respect to time of the vertical displacement. And then we obtain the following equation of motion. It's E times I, Wxx, and then we take the second derivative here, plus, due to the negative sign here, plus mu Wtt, and that's equal to 0. So it's the same equation of motion you saw in the first video of the previous chapter when you exclude, or when you set f to 0, which you should not do, of course, for a bed drive, but just to derive that equation, and where you consider either the belt at rest, so that only this term appears, or where you neglect the other terms. Then you would arrive at the same equation of motion. And let me remind, there is a second one, because we have two principal directions for bending in the plane. This would be the one, let's call it the vertical direction, for example, and the other one would be the lateral direction. But everything depends, of course, on these principal axes. So this would be one principal axis, and there should be a second one as well, leading to the same equation, but probably with different constants here, with a bit of different bending stiffness, and of course also with a different ladder for the displacement. Yeah? So we want to solve that problem. Well, usually one solves it with the Bernoulli separation approach, as you have seen in the previous video. And well, to this end, we need some boundary conditions as well. So let's start first with the equation. That would be the equation of motion. And then let's have a look at the boundary conditions. Well, The beam is now, the blade is now a cantilever beam. So it has a fixed end at x equal to 0. We start with the x coordinate. So the displacement and the first derivative of the displacement should be the 0 there. And it has on the other side a free end as a cantilever beam, where the second and the third derivative of the displacements are equal to 0. So with this we would have the equation of motion and the boundary conditions. And then we need, as it is an initial boundary value problem, we also need initial conditions for the deflection, so for W, and the transverse velocity of the beam. So we need W at all the positions x for one special time, t equals 0 or t equals t0, and we also need the velocity, so the first derivative of W with respect to time at any position x for one time t equal 0 or t equal t0. Well, the assumptions when we want to solve the problems here are that the bending stiffness is constant and also the linear density mu, so the product of the mass density O times area A is constant, so that that derivative extends only on W on the deflection here. So then we can introduce a dimensionless coordinate in order to, well, better represent our solution. So we normalize x, the independent variable here, by dividing by L. So we normalize the interval to 0, 1 instead of having 0 to L. And for the derivative, this leads to a partial derivative of 1 divided by L, which would be d xi by dx and d by dxi. And so if we replace the derivatives with respect to x by derivatives with respect to xi, we have to divide the first term by L in fourth power. You can see this here. And then we can at the same time divide by mu, so that we get one constant, and that would be EI divided by mu L in fourth power. So we can be sure that this will be the important constant. So for example, also for the natural frequencies, this will be the important constant. So if you change the bending stiffness and you change, well, in the same way, keep in mind, for example, that fourth power here, L, then you see that there will be no effect. So if you change L, if you double EI, for example, and you change L, well, in such a way that the ratio EI divided by L in fourth power is constant, then the natural frequencies will not be affected by this change. That you can deduce already from this way to write the equation of motion. Now we want to solve it by Bernoulli separation. And well, this approach is classical and has been also followed in the last chapter, previous chapter. And therefore, I would just repeat briefly the steps. So we split our deflection field into two parts by introducing two functions. One function that governs the space dependence, the other function, theta, that governs the time dependence. We insert that setting into the equation of motion and gather all terms that depend on psi only on the left-hand side of the equation, all the terms that depend on time only on the right-hand side of the equation, as we are allowed to change space and time independently in our consideration. We deduce that the left-hand side and the right-hand side must be constants. We introduce a constant minus omega squared here. The negative sign has been chosen because the positive sign would not lead to more meaningful solutions. We then get two ODEs. The first one is well known to us. It's the ODE of a single degree of freedom oscillator, free vibrations, free undamped vibrations. And the second one is a fourth order ordinary differential equation that governs the space dependence expressed by the function capital W. For the time dependence, we know the response. We know that the solution is A cosine omega t plus B sine omega t, and therefore omega here plays the role of the natural frequency. It determines the natural frequency of the time-dependent behavior of the response for our deflection field. But we do not know the value of omega, and it cannot be computed from some constants. It has to be determined from the boundary conditions, namely from solving the boundary value problem for the second ODE, where we have a free parameter omega, and omega has to be chosen such that we get non-trivial solutions. This will be done on the next slide. So we have to study the eigenvalue problem. We introduced therefore a nice shorthand notation for that constant. You see that I introduced the lambda in fourth power for that constant, already knowing that I have to take here the fourth derivative of some expression that will be an exponential function, leading again also here to a fourth power, and that we then will equate two fourth powers. Makes sense to choose as abbreviation not lambda for that constant, but lambda in fourth power. Before we solve that eigenvalue problem or discuss that eigenvalue problem, we have to transfer the boundary conditions to W. So from lowercase w to uppercase w. So the boundary conditions, well, on the left end, so at psi equal to 0, we have the fixed end. So the displacements are 0, therefore capital W is 0, and its first derivative is also 0. And for the opposite end, which appears now at psi equal to 1, due to the normalization, we have the second and the third derivative. These derivatives now refer to psi, that primes. We have that the second and the third derivative vanished. We solve the differential equation, ordinary differential equation, by the classical exponential approach, because it's a linear ordinary differential equation with constant coefficients, and then this approach yields the general solution. Well, it clearly amounts, if you plug in that approach into the ordinary differential equation, thus take the fourth derivative, to an equation chi in fourth power is equal to lambda in fourth power, leading to, again, two real and two purely imaginary eigenvalues, namely plus or minus lambda and plus or minus I times lambda. From the purely imaginary eigenvalue, we know that they create cosine and sine function via the Euler equation or Euler theorem, Euler formula. And the real solutions, purely real solutions, generate hyperbolic sine and hyperbolic cosine functions. And they are allowed here because we are considering the space dependence, which is on a finite interval between 0 and 1, and not the time dependence, where the time would grow until infinity, theoretically at least. Oh, cannot wait such long time. Okay, so our general solution, therefore, is now composed by four terms: by a sine harmonic with respect to lambda, a cosine harmonic with respect to lambda psi, and a hyperbolic sine and a hyperbolic cosine function. So as we are dealing here with the same value of lambda, we always find here as an argument the product of lambda and psi. Now it comes to the evaluation of the boundary conditions, and thus to finding a probably transcendental equation that governs the eigenvalues, which would be at a first step lambda, and from lambda we would deduce the natural frequencies omega. This would be the way we dealt with that problem in the previous chapter on belt drives. So we follow the same approach here. So Let's have a look at the boundary conditions. First, we evaluate the boundary conditions at xi equal to 0. Much easier to do. So we see that we get a2 and a4, the cosine and the cosine, hyperbolic cosine that are equal to 1. The sine function, the hyperbolic sine function vanish if the argument is 0. So we get a2 plus a4 must be equal to 0. So a4 is minus a2. And from the second one, by taking the first order derivative, we get lambda a1 plus a3 is then equal to 0 because the sine function switches, or sine hyperbolic switches to the corresponding cosine and cosine hyperbolic functions. And the cosine and cosine hyperbolic cosine switch to sine and hyperbolic sine. Yeah? So therefore we get a3 is equal to minus a1, and thus we have reduced the number of integration constants, the number of unknowns in our problem, to 2. Which makes sense because we already evaluated 2 of the 4 boundary conditions. Yeah? So we can, as an intermediate result, write our unknown function capital W, which governs the space dependence of the solution, now with just 2 integration constants. I've chosen a1 and a2 here. So we have a4 is minus a2 and a3 is minus a1. So therefore we have a1 sine lambda xi minus the hyperbolic sine lambda xi and a2 cosine lambda xi minus the hyperbolic cosine of lambda xi. Now let's move to the free end. So for the free end at xi equal to 1, we then have from this representation, which makes it much easier to deal with that case where the equation become a little bit longer. We have then lambda square a1, and we find minus sine lambda minus sine hyperbolic sine lambda. So we just evaluate that expression taking twice the derivative, and you can see that this leads to a change in sign for the sine term and also for the cosine term here, but to no change in sign for the hyperbolic functions, of course. No? And due to the inner derivative, there's a lambda squared here in place. For the third derivative, we have then lambda in third power here. And again, the sine function switches to the cosine function and the minus cosine function to a sine function. And hyperbolic sine yields then, the derivative yields then the cosine, hyperbolic cosine, and hyperbolic cosine, the derivative yields then the hyperbolic sine function. So this would be the 2 equations, and they form a 2-by-2 system for the 2 remaining integration constants, namely for a sub 1 and a sub 2. So this is an algebraic system, and this algebraic system can be written with in matrix shape, so with the coefficient matrix times a sub 1 and a sub 2, the vector a sub 1 and a sub 2, and on the right hand side we find zeros. So it's a homogeneous linear algebraic equation, and we need non-trivial solutions, otherwise the 4 integration constants are equal to 0, and these non-trivial solutions are obtained if the coefficient matrix is singular. The singularity of the coefficient matrix is equivalent to the vanishing of the determinant of the coefficient matrix. And now you can see that in the determinant, for sure, lambda will not appear in a classical polynomial, characteristic polynomial, but in a transcendental equation, because it appears inside the sine and the hyperbolic sine functions, inside the cosine and the hyperbolic cosine functions. So let's derive that characteristic equation, which would be a transcendental equation, on the next slide. So this would be my coefficient matrix here, coming from the linear algebraic system for these 2 integration constant a sub 1 and a sub 2. Well, if you do the computations and you apply the trigonometric Pythagoras here for the sine functions, cosine with a positive sign, and you can do the same. You see that the mixed terms, so where you have a hyperbolic function and a trigonometric function, that they cancel. here the same. Here I have minus cosine. No, here they remain. Sorry, they remain. For the sine functions, they cancel each other. For the cosine, here you have twice the cosine, hyperbolic cosine, cosine lambda, and cosine lambda. Hyperbolic cosine, cosine lambda. So they appear twice. And we also have here the addition theorem for the hyperbolic functions. So sine, hyperbolic sine of lambda and squared, and the hyperbolic cosine lambda squared with the positive sign minus hyperbolic sine function with the negative sign. So in total we will arrive at this result is therefore not correct. It's 2 plus 2 cosine lambda hyperbolic cosine lambda, and then you divide by 2 to get this result. And this would be a transcendental eigenvalue equation, and it has then also countably infinite many solutions. They cannot be evaluated well analytically or something. I can show you the result of the first eigenvalues. They can be ordered, starting with the lowest one, and the precision is here on 3 digits. So you can only compute them approximately. These would be the eigenfunctions. Now the eigenvalues, the eigenfunctions, so the mode shapes, they have to be obtained, well, by relating the 2 integration constants. Well, this can be seen from, well, one of the 2 equations. They are then, if that determinant vanishes, these 2 equations become linear dependent. So we take one of the equations, for example, the first one. No, I think I took the second one. Okay, and then let's take the second one. It's you multiply cosine lambda minus cosine lambda minus cosine hyperbolic cosine lambda by a sub 1. You multiply sine lambda minus sine hyperbolic sine lambda by a sub 2. In order to obtain a sub 2, you then have to divide by sine lambda minus hyperbolic sine lambda, which then appears in the denominator, and you have to put this term on the right hand side all together with the a sub 1, and therefore it appears here with a positive sign in the numerator, cosine lambda I plus hyperbolic cosine lambda sub I. And the index I refers now that this equation is valid and holds for any of these infinitely many eigenvalues. So for each eigenvalue I get a mode shape, and for each eigenvalue the relation between A2 and A1 is therefore different. So in order to get now the mode shape, the function W index I for eigenvalue lambda sub I, we have to insert everywhere, of course, an index I, and then we have to insert for A2I that relationship to A1I. So then I have to multiply that function with some constant. So there's some normalization constant, that A1I that has been set to 1 here. So this would be the mode shape. And now you see already one difficulty. Well, maybe 2. It's very long, that expression, but that was not the difficulty. But when it now comes to the orthogonality of these mode shapes of these eigenfunctions, it's difficult to see, also due to the appearance of that constant here, but also to the appearance of sine functions and hyperbolic sine functions, and several of them, that these functions are really orthogonal. So we need a better method to determine the orthogonality of the eigenfunctions. This will be, I would say, the remainder of that video to discuss this problem. But first, let's, well, follow the steps in the sense that we assemble the complete solution, and maybe then I would like to visualize some of these mode shapes, and then we discuss the orthogonality. Yeah? So the next step would be to assemble the complete solution, which now is for each mode the space dependence, so the mode shape times the time dependence, in which, well, the second part of the mode sits, namely the natural frequency. And once again, the natural frequency omega I is related to lambda I by the equation we saw that includes all the parameters of the system. So, and here you can see these first three mode shapes related to the first three eigenvalues here. So the fundamental mode is just like this. So it's somehow it must be 0 at one end, and then you see that somehow the deflections increase. For the second harmonic, well, there is at least a local maximum and there is a zero crossing, so which corresponds to a node of that vibration mode and, well, to a local maximum of the vibration mode. And for the third harmonic, we have two local maxima and we also have two nodes here. So guess what you would get for the fourth harmonic? You would get 3 local maxima and also 3 zero crossings. So you always get, well, if you consider mode number n, you would get n-1 zero crossings and n-1 local maxima of that mode. So these maxima and also the knowledge of these zero crossings are very important when it comes to measurements. So for example, if you want to determine the natural frequency of that third mode and you do your measurements of the response at the points where you have the zero crossing, then you will not see anything in your measurements or just some noise. You will not be able to determine, well, at least not reliably determine that a natural frequency corresponding to the eigenvalue lambda 3. You need to measure close to the local maxima. And therefore, that knowledge and that theoretical knowledge, at least, either by some analytical solutions or by some finite element structural analysis that you do beforehand, is very important for the measurements. The measurements should not be seen independent of any knowledge on the structural behavior. Otherwise, you risk to miss some important modes here. So with this, well, the last step would then be to adapt the solution to the initial conditions. I will skip this step insofar as I think you know the procedure quite well. Once you would have the orthogonality relationship, so you would multiply, you would evaluate the complete solution for time t equal to 0, if the initial condition is given for time t equal to 0 at least. So for the time where you have the initial condition, you would evaluate the complete solution and also would evaluate the velocity obtained from the complete solution, would set this equal to the given functions in Xi. And in order to determine these integration constants, two sets of integration constants that appear here, you would have to apply orthogonality relationships. So you would multiply both sides of the equation by some mode shape, Wj for example, and then integrate between 0 and 1. So with respect to Xi, would integrate. And if you get, if you have an orthogonality relationship for these mode shapes, you would then get from the complete solution a representation including this only theta sub j. And from theta sub j, evaluated of course at t equal to 0, you would then get aj, being the projection of that function, displacement for the initial condition, on the mode shape, on the appropriate mode shape wj, with which you multiplied, and then of course integrated, therefore the projection integrated from 0 to 1. That would be the procedure. But the crucial point is, do we have an orthogonality relationship for that function capital W? And I will show that there must be orthogonality between these mode shapes. And well, this is studied here by integration of our equation of motion. So it's generic, it sits already, that information sits already inside the equation of motion. The equation of motion will guarantee that the orthogonality relationship must be satisfied. It's a property of the equation of motion. That's the important thing you should learn here by this argument. So therefore I multiply the equation of motion with some function v. Of course, both sides of the equation of motion. We put the inertia part on the right hand side, therefore with a negative sign, and then I integrate from 0 to 1. Well, in order to move in the direction of some orthogonality relationship, I would like to have something symmetric. So interpret these terms as some kind of scalar products, something symmetric on the left-hand side with respect to the derivatives. So I will want to shift two of the derivatives with respect to psi from w to v. This can be done by partial integration. However, partial integration would introduce some boundary terms. And you could say, as I'm a lazy person, no, for later purpose it makes sense to avoid these boundary terms. Well, and therefore we have to carefully look at the boundary conditions here, whether we can apply the boundary conditions so that these boundary terms in the partial integration vanish. For the upper boundary, that's clearly the case due to the boundary conditions we have for w at psi equal to 1, namely the third and the second derivative will vanish. For the lower boundary, well, this would be the case if v satisfies at least the geometric boundary conditions, so at least the boundary conditions at psi equal to 0. Therefore, we assume, or we just put, that these functions v are then, so the space of function v is then shrinked to those functions that satisfy the geometric boundary conditions of our problem. So the two boundary conditions at psi equal to 0. So we cannot use any function v here, but just a function that has that additional condition satisfies this additional condition, namely the geometric boundary conditions at psi equal to 0. And then we can integrate, partially integrate twice. As we integrate partially twice, the sign will change to a negative sign and then back to the positive sign again. And we move two of the derivatives to v. Yeah, that's the advantage. Now let's put everything together. This would be the result after that partial integration. Yeah? So a very nice expression. Now let's move from w and v to Bernoulli separation, because we want to show a property for the mode shapes, so for the capital W's, and then this is the point where we introduce capital W. Now we replace lowercase w and lowercase v by one solution that is, as the general solution is a composition or superposition of all possible solutions of all the mode shapes. We just pick one mode shape for w and we pick another mode shape, so to prove orthogonality, for v. That's done on the next slide. So we replace v and w by one product of capital W j, theta j, and v and w by one product wk theta k. On the left hand side, you see that then you get a nice symmetry. You have under the integral the second derivative of wj and the second derivative of wk, and we have theta j and theta k outside the integral because they are time dependent. So this is the space dependent part. Well, if e and I happen to be constants, then of course you can also put them, well, in front or outside at least of the integral. On the right hand side, the same, we insert the modes. So we have in the integral the product of wj and wk, which is then multiplied by theta j, and pay attention, the theta k carries two dots. Theta j does not carry any dot because it's the product of the second derivative of w times v. We multiplied both the left and the right hand side with v. The only thing is that on the left hand side, we, by partial integration, we obtain two derivatives of the function v. Yeah. Now, therefore, we look at the time dependence here. And we know that the time dependence, well, is satisfied if we apply Bernoulli separation by a classical relationship between the second derivative, the acceleration, and, well, the stiffness term, I could say, so the restoring force term, for the single degree of freedom oscillator, or for free vibrations. Namely, the acceleration term is equal to minus the natural frequency, omega k squared theta chi. So let's insert this into this equation. Then we get the following equation. So on the left-hand side, nothing is changed. On the right-hand side, we have to change the sign. We put omega k squared outside of the integral because it's space independent. We now have theta j and theta k here. And we have the integral from 0 to 1 mu wj wk d psi. And now I would like to ask you to really look carefully, I would say with the eyes of a mathematician, on that equation. With the eyes of a mathematician means the mathematician always looks for interesting things of an equation. And the interesting thing in that equation, and that's why we did here, for example, the manipulation with the partial integration, is let's have a look at symmetry. That equation at the first glance would appear to be perfectly symmetric on the left-hand side. You can exchange the index j and k and nothing would change here. You can do the same here with theta. You can of course do the same here with the theta. You can do the same with the w's appearing here. You can change the indices j and k and nothing would happen. Except for one point. Do you see it? There's one point which escapes from symmetry. It's the omega k here. That coefficient carries solely the index k. And if you change everything, well, this omega k would be unaffected. So therefore, by changing the roles of, I could say, of v and w, or by assigning to v now the mode wk theta k and to w the mode wj theta j, I can derive a second equation for which the left-hand side is completely identical to this left-hand side, for which the integral on the right-hand side is completely the same as here, but for which the index of the omega k has to be changed to omega j. That's because this guy is symmetry breaking. Yeah? Everything else here in that equation, you can see it already from that equation. Yeah? Everything is symmetric, is nice, yeah? But for one term you had theta j, for the other term you had the acceleration theta k, and that breaks symmetry here because the acceleration is related to minus omega k squared theta k. So what would you get if you have such a second equation? You would get this one. Now what would happen if you take the difference of these two equations? Very clearly the left-hand side is equal to 0, but the right-hand side isn't, because usually the natural frequencies of mode j and mode k are different. Not only usually, but that should be the case. Sometimes you have double modes, but this is not the case here. So we assume that they are well separated. Our natural frequencies are well separated. So we would obtain on the right-hand side just the difference of these natural frequencies, which is non-zero, which is then multiplied by the same integral. And therefore we conclude, you can see it, we have the difference of the two natural frequencies, which is then multiplied by this integral, which is clearly the same. We just drop already the theta j and theta k and also the L in fourth power by division. And from that we conclude that now this integral must be equal to 0 because omega k is not equal to omega j if k happens to be not equal j. So from this we conclude that the integral mu times wj wk is equal to 0. If mu is a constant, then we would conclude that the two modes are orthogonal. And that's not the only orthogonality relationship you can obtain for that problem. Well, you could do the same, but with a different role. Namely, if you look at that equation once again, well, no one prevents you from dividing the equation by 1 divided by omega k squared, so that the omega k moves to the left-hand side. And then the right-hand side is nice and perfectly symmetric. And for the left-hand side, you would have a nice and perfectly symmetric integral, but the symmetry is disturbed by the factor of 1 divided by omega k squared. And of course, you will do the same with the second equation, where you have 1 divided by omega j squared. And as omega k and omega g are non-zero, natural frequencies, and as they are not the same, you can deduce a second orthogonality relationship. This is done on the next slide. So we divide our equation by omega k squared and omega j squared, and then we add them up again, and we get an orthogonality relationship for the second order derivative times bending stiffness. So if bending stiffness is constant, you would obtain a second orthogonality relationship, namely for the second order derivatives of the mode shapes. Yeah? That's shown here. Yeah? So, perfect. We have even obtained more than we expected. We have two orthogonality relationships instead of the one we need, namely for the mode shape itself. We also discovered that there is some more already hidden in the ordinary differential and the partial differential equation of our problem. Now let's apply that, no, not that one, the first orthogonality relationship in order to determine the constants of integration, and just to show you once again that we follow the same procedure as in the previous chapter, and also the same procedure that is the general idea of Fourier theory. But instead of doing Fourier theory with the classical Fourier projection functions, the sine and the cosine, so the harmonic functions, we are now able to generalize this to our eigenfunctions due to the orthogonality property. And that problem, the bending beam problem now, stands as a representative for many, many other continuum vibrations problems, where you obtain mode shapes and where you can deduce already from the properties of the partial differential equations that these mode shapes are mutually orthogonal, and therefore you can generalize Fourier theory from harmonic functions to mode shapes in continuum vibration theory. That's very important to retain. Yeah? So just let me show you how to follow these steps for the determination of the constants of integration. I mentioned this at the previous slide. So you evaluate the initial condition, let's say for time t equal to 0. So we have then a sub I, the cosine will be cosine omega t will then be equal to 1. Therefore the a sub i's and the sine harmonic terms, sine omega t terms, they will disappear because the sine of 0 is 0. So we have a sub I wi, and we want to determine this a sub I. We multiply by some mode wk. If you have non-constant mu, you can also multiply by mu at the same time, and then you integrate with respect to xi, and then due to orthogonality you would obtain for the right hand side, you would obtain just the product of omega k here and ak. Yeah? So you would obtain ak times mu k psi squared integrated from 0 to 1. So just one of these coefficients in that sum. Yeah? And you can determine that coefficient, and it is then mu for that function lowercase w psi at t equal to 0. You put in your prescribed function, let's call it f of psi here, multiply by mu, multiply or project on the kth mode and integrate it from 0 to 1. And finally, this ratio of these two integrals will be your a sub k. So you see that this is a series expansion that is completely analogous to Fourier theory, but with respect to mode shapes, and it works analogously not only for the displacement, but also for the initial velocities, which would allow you to determine the b sub i's. Well, with this you have already seen some, I would say, some extension. It's a repetition of the approach we saw in the previous chapter for continuum vibration, the Bernoulli separation method, but an extension in the sense that we need specially applied boundary orthogonality conditions here in order to be able to determine the constants of integration. Now the next question is, well, not only the determination of the integration constants is a little bit more complex here due to that orthogonality relationship, but the mode shapes look more difficult, and also the determination of the natural frequencies, or first the eigenvalues, is difficult because we have to solve a transcendental equation, and we are only able to solve it, well, in some exceptional cases, sine harmonic, cosine harmonic functions, but in general cases we are only able to solve it numerically and just up to a few digits. And for perhaps even more complicated problems, keep in mind that I assume constant bending stiffness and constant linear mass density, so mu times rho times a to be constant. Suppose you would have not constant conditions there, or we come back to one of the central assumptions at the very beginning, that you have a space dependence, position dependence of the principal axis of bending, then the equations would be even more difficult to solve, and therefore the question is can we derive bounds? Can we derive bounds for the natural frequencies, an upper bound and a lower bound? And this is shown to you in the next video. Thank you very much for watching this video.